Hi, this is Paul Gregg, and I'm going to make what I think is my final video of my documentation of my research and development efforts over the past year on backyard roller coasters. So this specifically is the development of my second cart that goes on my large roller coaster, the three-dimensional roller coaster, and developed an eight-wheel cart. I did develop a four-wheel cart before, but I wanted to carry more load, so uh, you've seen this before, but I'm going to be talking about different degrees of freedom. And a roller coaster cart is just like an airplane. If you're spinning this way, the wings are tipping up and down. We call that roll. If the nose is pitching down or up, we call that pitch. And if you're on a turn, a flat turn, and the roller coaster cart is just spinning around a horizontal axis, spinning around a vertical axis in a horizontal plane, then we call that yaw. So familiarize yourself with that. And I was trying to use just four wheels, and the cart I made with four wheels worked really well. It has a very light weight, so the responsiveness of the bogies really nice. I did a kind of an odd cart. I had Bogey steering on the front and Ackerman steering on the back, and you can look at another video to see what that's all about. But on this one, I decided I wanted to carry more weight, so I had 8 main wheels, and it involves these two-wheel truck assemblies. And in another video, I cover dynamic stability, why this this pivot axle is a little bit in forward of the center of the two wheels, and why it's a little lower than the other ones for dynamic stability. And this over here is the front mechanism that gave me yaw and roll pivot freedom. And I still use that, but I thought this was I thought I could do better than this. I'm not sure I did, but anyway, here's the documentation. So I spent my career in aerospace working on CATIA, a good CAD program, but they cost $10,000 a year for a license. And so until I can figure out how to get a really good CAD program, I'm using what's called FreeCAD. It's a free CAD program. Maybe it's difficult for me to use, but kind of got the job done. It crashes quite a bit, but got the job done. So at the end of this presentation, I'll go into FreeCAD, and CAD's nice because you can kind of design things up and take a look at things. I'm the kind of designer that takes sometimes 10 or 12 different designs, but that's okay. You kind of looking at load path and constraints. And here we obviously want to carry the load from the person's body down to the track through mechanisms that turn in all the right directions that we want. And we also want to keep the center of gravity low. And I don't know if I did a very good job of that with these designs, but there's always next time. So this was an early concept. You can tell I keep track of the concepts with the part numbers. So this is Backyard Roller Coaster Cart 3-dimensional-03. And so there was obviously an 01 and an 02 that I discarded, or I just leave them in a file and come back to them if I want to later. So configuration control is what we call it in engineering, where 2 years from now, if I want to know, if I wrote the part number on my card and I want to go find the CAD file, I can just search on a file and go bring up the assembly that is the same part number. So configuration control is an important thing about keeping track of what you did. This is just an example on the front joint where I want the 2 degrees of freedom. I thought the one I had last time was not quite very strong, and I wanted a more direct load path. So I was looking at what I call universal joints, some kind of a welded sleeve system with a built-up pin there. This is another concept where I had some flanges on the side. I think it's okay to go through thin metal, but I'm always putting thick welded in steel sleeves on, and I think that's working out pretty well. Here's another one. The frame's up here, and I have kind of a you can see this is it's just really just a threaded pin on a clevis kind of a thing. And then here's a kind of a concept that I thought was very interesting for the pitch freedom on the truck assembly out here, the two wheels on a little frame, and we call that a truck. And then this whole crossbar with the two trucks on it, we call that a bogey. Good design is all about looking at the load path and other constraints, and you can come up with there's tons of ways to solve one problem. So this probably is not the best way, but there's a bunch of ways. So here's kind of at the fourth iteration what my the front end of the bogey, the wheel assembly looked like. It's kind of tall. What you can see, what I'm trying to do is avoid open holes in tubular structure. Tubular structure is going to be naturally lighter than just thick angles and stuff. So I'm trying to stay with tubular structures, and I think I'm onto something in that you can weld the sleeves onto the side or through holes in the tubular structure and avoid an open hole, which is kind of a weak spot in design. So kind of with that mentality, and I'm kind of going through these designs. This one seemed a little tall. Maybe this was last January. I don't remember all the details of why I kept changing, but this one is another design you can see. And I think I did some, all the way along, I do a little bit of stress calculation to make sure I'm not doing something dumb. Usually things, if they look like they're not going to hold load, with experience, you think that doesn't look very stiff or doesn't look very strong to me. But it is good to quantify that with analysis. But you really need to go and take some college level strength and material courses to be able to do that well. So best to just overbuild it, I guess. And so this is the one I settled on. Pretty much, I think I did a little modification after the computer-aided design work. So there it is in FreeCAD, and then I built kind of one prototype and tried it out on my track. You can see I just tack welded these for temporarily, and I make a good fillet weld in there. Always try to use fillet welds. They're stronger than butt welds. We'll cover, I think there's another part that covers that a little better. So you can see these welded sleeves. Whenever I put a hole through a thin tubular member, I've also put a sleeve through it and put a fillet weld around it, so it's very strong and very stiff. Dynamic stability, the pivot axle is a little in front of the center of the two wheels for a little bit of stability. This would be forward over here. And the pivot axle is a little lower than the wheel pivot axles for a little bit of stability. I'm not sure if that's necessary. Stability is an interesting thing. Sometimes if you want it responsive, you have to kind of almost go unstable dynamically. But I'm kind of switching from soft skateboard wheels to harder roller skate wheels here, or something harder wheels with less friction on the track. You can see this will pitch pivot pretty well. I ended up making a mistake here. I'll talk about it later. As good as computer-aided design is, and I just make a sketch and put some dimensions on it from my computer and take it out to the shop. As good as computer-aided design is nowadays, nothing can beat getting out in the shop and mocking things up and putting things together and actually tacking a welded part together and seeing how you like it. And ideas really come at that stage too. So it's an iterative process. You can go back and use a computer-aided design and then come out and try to build something. And that's really the most effective engineering, in my opinion. So here's what ended up being iteration 6 of the 3D cart with the 8 wheels I'm trying to make. You can see the pitch pivoting truck here, side wheels, upstop wheel, and then this is the roll pivot pin, and then the yaw pivot pin is up here. This seems like a really good load path, though it did get kind of tall, and I paid for that later. I probably need to go a couple more iterations and try to get this hole squeezed down. These long members that are the frame, it's pretty far. It's 34 inches between here, and if you want to keep your frame light, you need to, this rectangular bar here, you need to put it standing upright, because that's where the moment of inertia is higher. It's stiffer and stronger and when it's standing up. And so it did get a little tall. These members here, I don't think I ended up doing this, but if you're going to cross members in the same plane, in the same space, the member that's holding the higher load, the more critical member, should have the right of way through here. So the yellow members are solid, and if I was going to put members across there, I'd be slicing up the gray parts, putting some parts in there, and then welding the cap on the top or something. I didn't end up doing that. It's too much trouble. So there's the front end. You can see this is ended up just putting a big bolt. I can't remember the size, but it's pretty big. I welded the cap of it onto this this U-shaped clevis that I made out of a thick piece of rectangular tube steel, and it's welded on there, and this is threaded up here. I never put threads in my models. I guess it's just obvious it ought to be threaded, and don't go to that detail. In a professional world, yeah, you got to have all that detail in there and call out what kind of weld you want and everything like that, but I don't do that here because I'm the designer and the fabricator. So here's putting the frame together. I have a welding table, get everything, exactly the way I want it, and then start putting tack welds on it. I don't know. It's nice to be able to have everything just exactly where you want it before you start welding. And so there's taken virtual to reality. To avoid butt welding this critical load path, I put these strips on here and just fillet welded around them. It got kind of ugly. I did end up paying them for that. In the track, these wheels rubbed on these a little bit, and I had to grind a lot of this welded part away so they wouldn't rub on there. I should have really, if I'd thought about that ahead of time in my CAD world, I would have moved these wheels a little bit further apart, and that wouldn't have happened. And then I philosophize a little bit about I think a good combination of computer-aided design and hardware mock-up is really a lot better than just one or the other. Couple of things here. I was having a lot of trouble drilling through thin steel with my drill press and a large bit. And so I found these step drills, and you make a small hole and then just keep stepping down. And in thin metal, it's I think a much cleaner way to make a hole. The other thing is these gussets here on the end. I could have put these inside and put butt welds on the ends of them, but this ends up, I think, a lot better if you make them a little longer and then put a fillet weld around the end. You can also put a fillet weld on the backside, and there's 4 of these things, top and bottom. So this corner joint is very stiff and very strong. Now, maybe there's a limit to how much welding you want to do, because weld wire costs a lot, and there's thermal distortion whenever you weld. But for what I'm doing right now, I think these fillet welds, wherever I can avoid butt welds, I put a fillet weld, and I think it's turning out better from a design standpoint. One problem was that the front wheels can have roll degree freedom. And so somehow the overturning roll moments of your whole body and the whole cart are going to have to be reacted into the track some way, this overturning roll moment, and that's got to happen at the back wheels. And so it's a real problem in that I have to have a bogie that can spin in the yaw axis but it still has to, when it's loaded, really highly loaded, when you're going around a turn and your body's being thrust to the outside of the turn, I have to be able to react that to roll moment or roll torque with some way. So I have to have some kind of a mechanism where this bogie can spin back and forth, and yet I can still react loads from the frame to the track. So I was coming up with different systems like that. I thought about a pin in a slot and grease it up, but I don't know how well that would work. I really wanted to employ some bearings somehow. So here's one concept I came up with just a pin in a slot. The slot would really have to be a lot longer than that, because this bogie pivots on my sharp corners on my roller coasters. It pivots, almost 20 degrees either way, and so this slot and plate would have to be a lot bigger than that. I thought about some methods I found online about a slider on a curved rail. Maybe you could just take a chunk of that and put it on either end and have these bearing sliders. That's one possibility. And then I came up with this idea that, well, what if I just stick a pin out there, stick a bolt out there, and put just a bearing on there, just one of my regular bearings. And then I thought, well, 2 is better than 1. This will help it in 1 degree of freedom hold. When it's totally turned out there, there'll be less load on it if there's 2 of them. So then I came up with this idea that I have this channel that I would put on the bogie, and then I think I turned it around and put the channel on the frame so that keep the bogie weight a little smaller. And so that's what I went with. I made this channel by welding 2 angles here in the corner, kind of fixtured it up well and welded that, and then cleaned the insides out really well so the bearings would roll on it really well. So I ended up welding this channel business to the frame up here, and then put the 2 bearings on the bogie so that it would be less mass on the bogie. So you can see how this design process, you kind of iterate and try things out and stuff like that. So that's what I ended up with. So here's the final design with the back end the way I wanted it. I hope I explained it well, that this lower crossbar of the bogie has to spin in a yaw direction, but it still has to take this overturning roll moment. And I hope I explained that well enough. But, I've seen people put just plates out here and grease them up or something. And the thing is, when you try this out on your cart, you gotta put it on your track and then push on it really hard, like it was the centrifugal forces were trying to tilt the whole cart over, and then roll it back and forth through a section of straight and curved, and see if this bogie here can freely turn while it's still under load from a overturning roll moment. And this worked pretty well. I have another idea where I could put 2 bearings up and down and have just a thin plate instead of this thick, heavy channel business. But maybe that's for next time. So here it is. I built the 4 of the trucks and built this whole thing and took it out to the track. And it really did work really well. You can see how much the aft bogie turns relative to the frame, and how necessary that is. My trucks and bogies are heavier than I'd really like them to be, and so the responsiveness is not what my 4-wheel cart is capable of. And there's every time these bogies turn back and forth, some energy comes out of my system, and so but they're about equivalent in as far as performance goes. The 8-wheel cart and the 4-wheel cart. It makes it all the way around, going really nice speed, and this one is much stronger than my 4-wheel cart. So I've let 130-pound people go on it, and we've sent 230 pounds around. So we could probably send more around than that. It's a very strong frame. The other nice thing about this system in the back is this 5/16 bolt here that's pivoting really doesn't do the heavy work. The heavy load, the heavy work is done through the bearings on the very end. And when you have a moment you have to react, the further apart those reaction points are, the less the local loads are going to be. So I'm not stressing some small bolt out too much here in the middle. So there's the final cart. It rolls around really nice. And then I built up the cart on top, put kind of a frame on the top. I wanted to keep the center of gravity low. I kind of already given up center of gravity. It's taller than I would have liked it to be, and I wanted to keep the person low. I put this sloped back on it. I found a piece of plastic at a company. They just gave it to me. I kind of thermoformed it and put it on with carriage bolts there. So, and then subsequently, I think I put on with contact cement, spray on contact cement. I put a rubber mat on there, one of those rubber mats you put in the bottom of a drawer, and so it's not slippery like this plastic was. Here's a test with some weight on it. Everything rolls around really nice. Putting the slope back on it there made the head clearance under my underpass much better. So last April, conducted a 230-pound dynamic test, heavy cart test. No signs of permanent deflection or material cracking anywhere on the cart or the track. So assuming a 1.5 factor safety, this qualifies this coaster, the track, and the cart for a 153-pound rider. I won't go through this in detail. Basically, I really like the concept of not leaving open holes in a thin tubular structure, welding sleeves either to the side of the tubes or through the tubes. I learned a lot about bearings. Bearings come, these are roller skate and bearings and skateboard bearings. They come ABEC 1 to ABEC 9. The higher the number, the tighter the tolerances are, the smoother everything is. And I found, the main wheels that you're going on, they're always turning. They spin up and they always turn, and you want the best bearings you can get in there, ABEC 5 or better. But I found out the side wheels, they're always spinning up and then stopping. They only work when you're going around a turn, and only the inside ones work. And so they're kind of spinning up and slowing down as you go through the roller coaster. So I just used cheap roller skate ABEC 1 bearings on that, and they seem to spin up quick. And so that's, I don't know if that's right or not, but it seemed to make sense. We won't go through any of that. And then I document the design changes I'd go on for another cart. At where I worked at Boeing, they had a certain phase in a program. The engineers always want to change things. It doesn't matter. They can have what you think is a perfect design. The next day they'll come in with 5 more concepts. And it's an old saying at Boeing where there's a certain point in a program where you have to shoot the engineers and build the airplane. And I guess, that's true. You have to build, at some point you have to say, well, this looks good enough, and we're going to go with it. And am I willing to spend a lot more time getting another 1% out of this design? If I've got 95% out of it, how much do I really want to spend in time and money to get that 96%? And I guess I can understand that, but still, don't think that the best designs are on products. There's always something better, always something you can do. So finally here, I'm going to bring up my FreeCAD program. It is a difficult program, but at least, you can make 3D parts with you start with 2-dimensional sketches. You make 3D parts. You can see, you can roll it around and have fun looking at things. You can see that I drew in a curve there for my smallest radius hump in the track, and then you can see how much clearance you have. So these are good things to do on a computer where you're not having to build the whole thing and then rebuild it. You can see each one of these parts is a separate file, and you can print this out. You can make it into dimension drawings. You can send it to machine shops. You can do all kinds of things. And computer-aided design is certainly a very, very useful tool. So You can even, I've even designed tracks on using this system. But anyway, that's it. I think that finishes everything I wanted to talk about for my research and development on backyard roller coasters. As in anything, riding the coaster at the end is, I'm sure, fun for my grandkids and stuff. But I think the process of designing and then fabricating something and seeing it in real life and iterating and making it better. My daughter has a saying, "The joy is in the journey," and that's really true. The it's the journey that's more fun than the destination, I think, a lot of times. So thanks for watching.